Hello guys, and welcome to my YouTube video. So we're going to be focusing on the May-June 2020 question paper 1-2 for physics, and the question paper is 1 hour 15 minutes long. So I'm going to be going in the questions in depth so that you can be able to understand and explaining each and every question and how it was supposed to work out. So if you do find this content useful, please like and subscribe to my channel and comment if there is anything that is unclear. Okay, so to start off, we're going to start off with the first question, which touches on a very, very important topic, the topic of reasonable estimates. So we've been asked to estimate the mass of a raindrop. How are you supposed to know this? Well, you're just supposed to guess. If we start with the first one, this is 10 kgs. 10 kgs, I mean, this is like a little bag of maize meal, right? Or a little bag of rice or something like that. How can one raindrop equivalent to this, right? It doesn't make sense. If we go to B, this is 0.1 kgs, which is literally 100 grams. Right? And it doesn't make sense. How can one raindrop be equivalent to 100 grams? I think that's like, I don't know, an apple. It's sort of a very small apple, right? It might be 100 grams or something. Then if you look at this, this is 0.001 kgs, which means that if you have 100 raindrops, right, you join them together, they'll be equivalent to the mass of a small apple. 100 raindrops. Guys, come on. That doesn't make sense. That doesn't work, right? And then if you look at D, this is 0.005 kgs. Sorry, these are actually 5 zeros, right? So it's 0.00005, okay, something like this. So if you look at D, right, this is 0.12345 kgs, right? This makes sense. This can be a reasonable estimate of the mass of a raindrop. But question 2, which quantity is a scalar? So basically, scalar quantities consist of two major properties. Okay, I call them two major properties. Number one is that they have magnitude. Can you measure it? Does it have magnitude? Magnitude just refers to size. Can it be measured? Number two, does it have direction? So if it ticks these two boxes, right, in this case, no direction, right? So no direction is basically what symbolizes a scalar quantity. Right, so let's put this, no direction, right? If it was a vector, it would have direction. Okay, so if we look at acceleration, acceleration is a vector, so that's out. Force is a vector, so that's out. Kinetic energy is a scalar, so that is our answer. Momentum is a vector, so that's out. Move on to question 3, we are given a galvanometer, and that is a galvanometer that is used in a now method. So basically, a now method is just used, to sort of show the direction of flow of current, right? So it's just used to show the direction, of current, right? So what you're going to do is you're just going to have something like this, right? So they're just going to consist, right, of a little arrow, and then that is going to deflect whenever there is a current that is going to be measured, right? So we want to protect it, right? And we want to protect it from what? Excessive initial current. So a lot of current might be able to flow through. And the whole role of the galvanometer is that we want to protect it. So we're going to use resistance, right? Resistance consists of resistance. The importance of resistance is that it stops, right? It stops a lot of things from actually, passing, a lot of current from passing through, right? That's the whole point of resistance. If it sees an electron, it stops that electron, right? Or it sort of reduces the motion of that electron. We've been told that the 0.5 is in series with the galvanometer. Okay, so if we have our 0.5 like so, right, it's going to be in series with our galvanometer, right? So if current is going to pass through, it's going to be stopped by this, right? Or it's going to try to stop as much current as it possibly can. Then it reaches the galvanometer. But mind you, this is excessive current. So is this the best that we can do? Maybe not. If we go to B, we have the 0.5 in parallel with the galvanometer. So the 0.5 in parallel with the galvanometer, and then in series with a 1 kilo ohm, right? This is 1000 ohms, mind you. So if current is going to come, this 1000 ohms is going to try its best to sort of stop some of the current. 1000 ohms, that's good. Then if you arrive here, current sort of likes the path with least resistance. And if you look at this circuit, this is sort of the path with the least resistance. So it's going to favor this path. So you sort of avoided a lot of current from reaching the galvanometer. So this could work. And then if you go to C, if you look at C, right, we have the 1 kilo ohm resistor in parallel, right? So we have the 1 kilo ohm resistor in parallel to our galvanometer. like I've said, current likes the path of the least resistance. So the path of the least resistance is the one with the galvanometer with 5 ohms. So we're literally exposing this galvanometer, and it's going to experience a lot of current. So this is not the best. And then, as we have seen, that A is not the best, right? Because in B, we're first passing it through 1000 kilo ohms, right? Then if you go for D, okay, we're going to have the 1 kilo ohm in parallel, right? So we're going to have a 1 kilo ohm in parallel with our galvanometer, okay? But then we're connecting it in series with the 0.5, right? So current is first going to fall through the 0.5, but it's not going to do as good as a job as the 1 kilo ohm. Then it's going to follow the path of the least resistance, which is the galvanometer. So this really doesn't help us at all. So the correct answer has to be B, because it's going to first try and stop the current with its 1000 kilo ohms. Then it's going to go through the path of the least resistance, which is here, most of it. Then some will arrive at the galvanometer. Question number 4. Readings are made from of current for different voltages across a fixed resistor. The results are plotted on a graph to show the variation of I and V, which best description indicates the type of error. Okay, so we have we have systematic error, right? Systematic error, a very important kind of error. And why is it important? Because it is constant. Okay, there is nothing constant as a constant, right? Number 2 is a random error, right? A random error is basically an error that is a scattering of values. Okay, a scattering of values. So if you look at this, our graph was supposed to be like this, right? This was supposed to be our initial graph, because we know that for a metallic conductor, I and V are directly proportional. So our graph was supposed to pass through the origin, but it's not. It's going like this, right? And if you look at this, this is a constant deviation. Okay, this is sort of a constant deviation. So this symbolizes only one error, a systematic error. If there was a random error, what was supposed to happen is that there was supposed to be a scattering of values about this true line. So if values were going to scatter, it would mean that we're going to have a random error. But in this case, it's only systematic because it's consistent, right? It's constant, and only mean that the instrument is at fault. So the correct answer is D. Move on, question 5. A stone is dropped from a height of 20 millimeters above water. So we have water. So I'm going to put my water surface here. Then we have a stone which is somewhere here at a height of 20 meters. So the area, right, of a velocity time graph basically symbolizes the displacement, right? The displacement that object has experienced. So if we're going to look at this area, right, essentially, so we have 3 areas. We have this area, and then we have this area, right? So those are our 2 areas. So if we look at this area, the area is the area of a triangle, right, which is half base times height. And if you look at this, this is half. Your base is 2, your height is 20, and that's going to be 20 meters. So it means it has fallen 20 meters. So basically, our stone is going to be here at the surface because it has fallen 20 meters. And if we're going to look at this area, right, this is going to be length times width. If we look at our length, 4 minus 2, that's 2, times our width here, which is 5. This is going to be 10 meters. So it means that it's going to move an extra 10 meters below the water surface. So it's going to be a distance of 10 meters below the water surface after 4 seconds of it being dropped. The correct answer, therefore, will be B. For question number 6, we're given 2 cars, car X and car Y, right? We have 2 cars. And then we've been told that they are a distance. So the second car Y is a distance d0 behind car X and traveling at a speed v in the same direction. So they're sort of moving. Then the speed of this car v, is actually less than the speed of u. At time t goes to 0, car Y begins to accelerate, but the acceleration is constant. Car Y overtakes car X at time t goes to t, which graph shows the variation with the time t of the distance d that is between these two cars. So if you think about it, what's going to happen essentially is that the car x is going to move. Let's say it's moving at a faster speed, right? Let's say it's moving at 100 meters per second. And then car y is going to move at a slower speed, which is, I'm going to say 10 meters per second, right? Based off my calculation. Okay, so car y is going to accelerate and then it's going to overtake. So if you look at this, this is a graph of distance and time. So we might use Newton's laws of motion, right? Thanks to, say, Isaac Newton, famous physicist, we have these laws of motion that can help us to solve these problems. Physics is just about problem solving, guys. Right, so what are we given and what equation can we create? So I'm given a constant acceleration, I'm given time, I'm given distance, and I'm given speed. What equation comes to mind? One equation is coming to my mind. I don't know what equation is coming to your mind, right? But one equation is S is equal to ut plus half at squared. And this is great because I have a variation of S, then a variation of t. Pretty cool. But if you look at this, this is actually a quadratic graph because of this t squared, right? Because of that t squared, this is actually a quadratic graph. And why do I say this? Well, if S is on the y-axis, I can put a y, right? U is any number, the initial velocity. Let's say it's 20, right? Our t is on the x-axis, that will be x. Plus half, let's say our acceleration is 10. For example, it's just an example, guys. So half of 10 is 5. This will be 5x squared. If you look at this, this is a quadratic graph. If you plotted this is supposed to have a quadratic shape, right? So it means that this graph is essentially just a quadratic graph. And what this means is that it's either going to be like this or like this, right? It's going to follow some sort of shape that is quadratic. Okay, so if you look at our answer, is this a quadratic shape? No, so it's out. A, is this a quadratic shape? No, it's out. So we're left with B, then we're left with C. These are the two possible quadratic shapes. But if you look at this, you want to figure out which one is correct. Is B correct? Is C correct? Look at the main difference. With the D, it's first going to increase. This is D naught. It's first going to increase to be more than D naught, then it's going to start to decrease. With C, it's just going to start to decrease from D naught. So I want to figure out which one of these two is correct or which one of these two is wrong. If you look at your question here, you have two cars that are moving. Car X is going to move faster than car Y. And if it's moving faster, it means that this D is first going to increase, right? Because it's sort of a game of catch-up, right? Car X is still moving at 100 meters per second. So it means that for a certain period of time, as car Y is accelerating, D naught is going to stop, is not going to stop, right? It's going to keep on increasing, right? As it increases, the gap between the two cars increases. There's going to come a point where car Y is going to have the same velocity as car X, right? So let's assume that car Y now reaches 100 meters per second. And at this point, D naught ceases to increase. It's now constant. If this speed now becomes 200, if this speed now becomes 300, then car Y is now faster. It's now going to start to overtake. Hence, it means that the value of D naught is going to decrease. So it first has to increase. Why does it have to increase? Because car X is still moving faster, guys. So the distance between them is just still going to increase, but it's still moving faster. If a person is running and you're walking, it means that the distance between that is going to keep on increasing, right? But if you begin to run also, right, and then you run, and you run at the same speed as that person, the distance between you will not change. But if you now run faster than that person, then the distance between you will decrease. That's basically the concept that was applied here. So basically, since it was quadratic based on this shape, I limited the shape using the quadratic fact. Then I chose B because it first has to increase before it decreases, before the speed becomes equal and the speed of Y actually increases. So the correct answer will be B. Okay, moving on to question number 7. We're told that the resultant force that is acting on an object is slowly increased, right? So the resultant force in an object is slowly increased, which graph could show the variation with time t of the momentum rho of the moment which graph could show the variation of the time t of the momentum of the object. Okay, so what you first need to understand in order for you to be able to solve this question is actually what is a resultant force. Okay, so basically, the resultant force is the rate of change of momentum. So it's the change of momentum divided by the time that will be taken for that momentum to change. So essentially, it means that the resultant force F will be equal to your change in momentum divided by your time t. So your change in momentum will be equal to your force times your time t. And if you look at this, if you have a graph of y that is equal to mx, right, you can easily see that will therefore refer to the gradient, right? So it essentially means that f is the gradient of a graph of momentum against time. But if you look at this, we're told that the resultant force is slowly increased. So this is just code to tell you that the gradient is increased. It is the gradient that is increased. So if we're going to analyze this question, if you look at this, we're starting off with a gradient like this. Let's start with A. So we were starting off with a gradient like this, but we're ending up with a gradient like this. So you can initially tell me that the gradient has decreased. So A cannot be a possible answer. If you look at B, our gradient is starting off like this. A very, very less steep gradient, almost zero. But at the end, we're going to end up with a gradient like this. Very steep, right? So it means that it's a higher gradient. So the resultant force, which is the gradient, is actually increased. So B is the correct answer. Let's look at why the other answers are wrong. If you look at C, you're starting off with a gradient like this, almost very steep. But you're ending up with a gradient like this, almost less steep. So it means that that is a decrease in the gradient or a decrease in the resultant force. If you look at D, the gradient is fairly constant, like so. It doesn't change, and if the gradient doesn't change, it essentially means that the resultant force also doesn't change. So the correct answer has to be B. This is where we're seeing an actual increase in the resultant force due to an increase in the gradient. Question 8. An astronaut has a weight of 660 when she's standing on the Earth's surface. So in this case, our astronaut is Mary. Hi, Mary.
Hi, Keith. I am happy to be your astronaut today and go to Mars.
So Mary is an astronaut, and Mary is standing on the Earth's surface, and when she's on Earth, she has a weight of 660. So the weight of Mary will be equal to the mass of Mary times the g on the Earth. Okay, so basically the mass of Mary will be equal to the weight of Mary divided by the g on the Earth. Because Mary is going to get on a spaceship, and then she's going to travel off to Mars, where the acceleration of free fall g is 3.71. So we just want to find the weight of Mary on Mars. So what we don't have about Mary is her mass, because if we have a mass of Mary, we can probably find the weight of Mary on Mars. So the mass of Mary would just be her weight, which is 660, divided by the g on Earth, which is 9.81, and this is going to give me 67 kgs. So when you now go on Mars, the weight of Mary will now be the mass of Mary times the g on Mars, right? The mass of Mary is 67, the g on Mars is 3.71. This is going to give me 249.6 newtons and so forth. So this is just going to be approx 250 newtons. So the correct answer has to be C. Move on to question number 9. A mass m1 travels with a speed u1, collides with a mass m2 that is traveling with a speed u2 in the same direction. Same emphasis on same direction. After the collision, mass m1 has a speed v1 and mass m2 has a speed v2, but in the same direction. And we're told that the collision is perfectly elastic. So I need you guys to understand what the word perfectly elastic actually means and what it entails for this kind of collision, right? So for perfectly elastic collision, one thing that you need to know is that momentum is conserved. So a very, very important key aspect is that momentum is conserved. And what this tells me is that the momentum before we collide should be equal to the momentum after we collide, right? So momentum before we collide is going to be m1 u1 plus m2 u2. That's going to be equal to m1 v1 plus m2 v2. So it means that m1 u1 minus v1 should be equal to m2 v2 minus u2. And if you look at this, this is b. Sorry, in this case it is c, right? And you can actually see that c is correct. But remember, our question is saying which one is not correct. From our question, which one is not correct? So it means that C cannot be a possible answer because you guessed it, it is correct, right? So C is going to be wrong. Another thing that I also know about an elastic collision is that kinetic energy is conserved. So this is the first thing that is conserved, right? Momentum is definitely conserved. But the second thing that is also conserved is kinetic energy, right? So kinetic energy is also conserved. Okay, so kinetic energy is conserved, right? So kinetic energy, you just find it by saying 1/2 m1 u1 squared plus 1/2 m2 u2 squared should be equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. If you multiply throughout by 2, you have m1 u1 squared plus m2 u2 squared should be equal to m1 v1 squared plus, if you look at it, we have m2 v2 squared, right? So if we were to put everything on one side, we're gonna have m1 u1 squared minus m1 v1 squared is equal to m2 v2 squared minus m2 u2 squared. If you look at this, this is A, right? So it means that A is correct, so A cannot be correct, right? Because the question is saying which one is not correct, so A will be out. And then another thing that I need you guys to know is a thing about relative speed of approach and relative speed of separation. So what you should know that is that for an elastic collision, the relative speed of separation should be equal to the relative speed of approach, right? And how do you find the relative speed of approach? I want you guys to know this important trick. If things are moving in the same direction, right, what are you going to do? You're going to follow what the S tells you. You're going to subtract their velocities. If you subtract two velocities, you're going to get the relative speed when things are moving in the same direction. Number two, if things are moving in opposite directions, what are you going to do? You're going to add, right? You're going to add the two velocities, right, in order for you to get the resultant velocity. So if you add the two velocities, you'll be able to get the resultant velocities, right? So in this question, they are moving in the same. So in this question, they are moving in the same direction, right? If you look at this, they are all moving to the right, the same. So it means that the relative speed is just a matter of you adding the speeds together, because it's just a matter of you subtracting the speeds together because they're moving in the same direction. So if we consider this, we can just say u1 minus u2. Okay, this should be equal to, right? If you look at this, v2 minus v1, right? We're just subtracting these velocities, right? And then you subtract to figure out which one of these will actually work, or which one of these will be similar to the answer that you are given. So if you look at this, if you put u1 on this other side, we have v2 plus u2 being equal to u1 plus v1. And you see that B is correct, so in this case, B will be wrong. And those guys are the three things that you're going to need: the relative speed of separation and approach, the conservation of momentum, and then the conservation of kinetic energy for an elastic collision. So it means that we have never talked about D, right? We know nothing about D. It doesn't match any condition that we know whatsoever. So in this case, D is going to be not correct. So in this answer, it was going to be the actual correct one. Very important for you to be thinking of that. Question 10. This is a question on electric fields. We don't cover electric fields, so we will not be focusing on that question. Question 11. A bicycle pedal is connected to a pivot. So we have a person riding a bicycle, right? And as they're riding a bicycle, they're applying a certain force on the pedal, because if you know a bicycle, you know a bicycle consists of pedals, right? Where a person will be sort of, stepping on those pedals, right? So we just want to find the moment of this force, right? What do we know? So always start with physics. What do you know? Right? We know that the moment of a force is basically equal to the force itself times the perpendicular distance from the line of action of the force to the pivot. So it's times the perpendicular distance. So if you look at this, what is our force? Our force 60 newtons times what is our distance, right? Guys, fetch this enough. We have this force that is going down like this. This is the line of action of this force. What distance is perpendicular to this, guys? It's this distance, right? This 16 centimeters is the one that is perpendicular. So it's going to be times 16 times 10 to the power times 10 to the power of -2. Then that's going to give you a moment of 9.6 newton meters, right? So the correct answer will be B. So I just needed you to know what exactly is the moment of a force and what distance we will be looking for when we're talking of that specific scenario. Question 12. A thin horizontal beam XY is freely hinged at point Y to a vertical wall. The beam is held stationary by a cable XZ, which is attached to the wall at point Z. The beam supports a weight W at point X, and then we're given the forces, which is FC and FB. Then we've been asked which vector triangle represents the forces acting on point X. So we are at point X, and we want to find the vector triangle. So let's first start with the easy one, right? The easy one that is very easy for us to identify has to be this, right? The force that is acting down, like so. So we're going to take this force, special force, and we're going to place it here. So basically this is our weight, which is going to be acting down. Then in the cable, the cable is going to have a tension, a specific tension T, acting in this direction. Why in that direction? So that it can be able to sort of override this weight that is acting down. So this tension is supposed to sort of, support the weight. So it has to be acting up so that it provides a force that supports the weight, which is acting down. It's going to look something like this, right? Something like this. And then if we take it, we're going to connect it head to tail, because this thing is in equilibrium, guys. If it wasn't in equilibrium, well, it wouldn't be remaining like this, as we can see from the diagram. It would either fall or spin or do something like that, right? So we're just going to take it, then we're going to place it like this because it's in equilibrium. Now, so this is our tension T, right? Or in this case, it's FC, right? So if you connect it here, in this case, it's actually FC. We're now left with a force in the beam. Okay, so this is a very tricky one. We want to figure out which direction is it acting. Mind you, I said that the resultant force is 0, and we know that for the resultant force to be 0, the triangle that you must form must be a closed triangle. That's the law. If it's a closed triangle, it means that the resultant force is 0. So it means that my force that will be coming from the beam should be acting in this direction. Why? So that it forms a closed triangle and the resultant force can be 0. Also, another very important reason is that you see the tension is acting in this direction, right? So it wouldn't make sense for for the force on the beam to also be acting in this direction, because that would mean that there is no force that will be acting in the left to counteract the horizontal component of this tension, right? So this tension is going to have a horizontal component in this direction. So we're going to need to have a force in that other direction to oppose that horizontal component of the tension. Or in other words, we just need to form a closed triangle like so. by joining our things head to tail, we just need to form a closed triangle. So FB should be acting in this direction. Okay, so it means that weight down, FC in that direction, FB in that direction. The correct answer will be A. Very important, guys, for you to be thinking of that. Move on to question number 13. A pipe is open at one end and it floats in a liquid as shown. So we're shown this diagram, and then we've been told that the cross-sectional area, underline what is important, cross-sectional area is 0.012. The weight is 32. And then we just want to find the density of the liquid. Ask yourself, what are you given and what do you know? Okay, I personally know something created by this guy Archimedes, right? A concept of upthrust. So I know that upthrust is equivalent to the density of the liquid that you're in times g, the acceleration due to gravity, times the volume of the object, right? Or the part that is submerged in water, right? What part is submerged in water? So basically, this is Archimedes' principle. If you want to find the upthrust, which is an upward force, if you want to find the upthrust, you're going to multiply the density of the liquid times g times the volume of the object, that part which is submerged in water. But why is this principle true? I personally don't like memorizing formulas without understanding where they come from, and I hope that you also feel the same way. So I'm going to explain just a little bit in 2 or 3 minutes what where this formula actually comes from. Okay, so if we look at this, let's assume you have an object, right? So we're going to assume you have a specific object like so. Okay, so this specific object, right, since it's in a liquid, it's going to experience a force. So it's going to experience a force that will be up here. Then it's going to experience another force that will be down here. But if you know anything about things that will be in a liquid, is that pressure increases with depth. Pressure increases with depth, right? So you can find the force acting on this because you know that pressure will be equal to the force at the top divided by the area that is exposed. So the force at the top will be equal to the pressure at the top times the area that is exposed. Then if you go to the bottom, the pressure at the bottom, therefore the force rather at the bottom will just be equal to the pressure at the bottom times the area A. Is this clear? Right. So the force at the bottom, however, is going to be greater because you know that pressure increases with depth. So this force is going to be greater because the pressure here will also be greater. But the differences in those forces is going to be the force that acts up with the thrust, right? So the up thrust. So that force which acts up is just going to be the differences in the forces that you're given. So your up thrust, right, as the name suggests, is just going to be the difference between the force that is at the bottom and the force that is at the top. So it's going to be the up thrust. The force at the bottom will just be the pressure at the bottom times the area minus the pressure at the top times the area. But the pressure will just be, if you consider this height of the liquid H1, then this height of the liquid up to here, and you consider that H2, the pressure at the bottom will be H rho G from the equation of pressure. The density of your liquid times G, but your H is going to be H2 times A, minus here we have rho G, but your H will be H1, this H1, okay, times your area A. You're going to factor out rho GA, you'll be left with H2 minus H1. But H2 minus H1 is just this height of this object H. So you're just going to have rho GAH. But AH is the volume. So your upthrust is going to be rho G times the volume. But it's going to be the volume of the entire object if it's fully submerged in water. If it's not, it's the volume of that part which is submerged in water. Right, now you know that, you know this fact. Where does this formula come from and all that stuff? Now we're just going to use it to help us find the density. So in this case, the density will be equal to the upthrust divided by G times V, right? But I have already told you guys that your volume V is just equal to your area times an exposed length that you have. But in this case, since it is stationary, there's going to be a specific weight that will be acting here, right, which is the weight of this thing. But like I've said, upthrust is an upward force, right, which is going to act up. So your upthrust is going to oppose this weight. But since it's not going down, it's floating, since it's not going down or just flying up, it means that the upthrust is just enough to be equal to the weight. So it means that in this calculation, my upthrust, right, is just equal to my weight. Okay? So it means that my density will be equal to my weight, which is 32, divided by G, 9.81, times my volume is my area times my length. Remember, guys, so my area is 0.012. My length is this length that is submerged in water. That is the only length that you need, which is 0.30. If you calculate this density, you're going to get somewhere around 906.10. You round it to 2SF, that's 910 kgs m to the power of -3. The correct answer will be B. Very important, guys, for you to be thinking of that. During an interval of time, fuel supplies energy to X to a car. So we have a Lamborghini, very fast car, and then during a time interval, fuel is supplying energy X. So the fuel that will be in the Lamborghini is going to supply energy X. Some of this energy is converted into kinetic energy. So as the Lamborghini will be moving, some of the energy will be converted into kinetic energy, specifically when the Lamborghini is accelerating. The rest of the energy Y is then lost, so we're losing the rest of the energy Y as thermal energy. What is the efficiency of the car? What do we know? We know that efficiency essentially is going to be the energy output. What do you get out? Right? The energy output divided by what did you put in. Even in physics, right? If you don't get anything out, even if you put anything, you're not efficient. Okay, so the energy output is what did we get out from this Lamborghini, especially from the fuel, because we want to find the efficiency, the rate at which the fuel is being used effectively. So the total usage will just be if we supplied X but we wasted Y, therefore we used X minus Y. How much did we put in? We put X. So X minus Y over X will be the correct answer. 15. In which situation is work done on an object? So we want to do work and want to do work on that object. If you look at 15a, the object slides with a constant velocity, so particular emphasis to constant velocity along a horizontal frictionless surface in a vacuum, right? There is no work that is done, right? There is no change in velocity. There is no no work lost in overcoming friction because it's frictionless. So basically we're not doing any work, we're just moving because there is no force that is being exerted. You go to B, you have a person trying to act as if they're muscle men. So they're trying to hold an object at arm's length. I don't know why, but they're keeping it at a fixed height. So since it's a fixed height, there is no change in displacement. So you're not doing any work, even if you're exerting a force to hold that object. But if there is no displacement, then there is no force. So there's no there's no work done. Then if we move to C, a person pushes the object up a frictionless ramp. So you're gonna have a ramp like so, and a person who's gonna push a specific object up that ramp. So basically, that person is gonna supply, right, gravitational potential energy to that ramp, to that object, right? So work is going to be done in supplying energy to that object. So as it moves up, work is actually done on the object itself. So the correct answer has to be C. Stationary object just partially floating in partially submerged water. No work is being done, right? Because you always have to ask yourself, is there any force being exerted? Is there a specific distance being moved? Hence work will be done. Question 16. A spring. We have a spring, right, that is attached, okay, at one end to a fixed point. A mass is then hung from the other end of the spring. The spring has extension X, so when it's hung, it's going to extend with an extension X. The variation of the tension in the spring with this extension is shown. Which statement is correct? Emphasis to correct. So I want to teach you a very important key concept, an important concept of understanding what the area of a force against extension graph entails. This area refers to the work that is done. Okay, it can be the work that is done in either extending the spring, okay, or it's the work that is done in compressing the spring. but however, work has to be done, right? So the area underneath this graph just basically tells me the work that is done. So this can be work that is done and then stored as the elastic potential energy, because we can store that specific energy, right? So mind you, because work done is force times a distance that has been moved. So in this case, the area of this graph will just be, half Fx, or half tension times extension, right? So it's just going to be half your tension times your extension. And because of that fact, it means that, we can eventually just find the work done just by looking at the area. So we want to find the area SPR. The area SPR is basically that area, and in this case, that is not the area that we shaded. So A cannot represent any energy whatsoever, because the energy that is stored is basically stored during the process of doing work. Area SPQR, this entire area, is this the area that we shaded, guys? No. So it means that B has to be wrong. Area SPQ, is this the area that we shaded? No. This area symbolizes nothing. And then, so how can you show us the loss of gravitational potential energy when that area doesn't even symbolize anything at all? It also means that C will be wrong. If you look at D, the area SQR, now we're talking. So this area SQR is the one that we actually shaded, and it does represent the elastic potential energy that we had stored in the spring, because we're doing work on the spring. So it means that it's going to store some of that energy that we are doing work with. Okay. Question 17. We're given an escalator. An escalator is basically something that makes work easier by just, people stand on those lifts and then they sort of transform them and transport them up. So we're given a very special escalator that is 25 people that are just standing on it, and it's moving at a very, it's a slow speed, fast speed, I don't know the speed that escalator is supposed to move with, but you just know it's moving the speed of 4.3. The average mass of that person is 78, and the angle is 40 degrees. We want to find the minimum power that is required to lift these people. So let's look at this more from a more physics perspective. So if you look at this, we have our slide, our something like this. This is our escalator, and then we're given this angle, which is essentially just 40 degrees. Then we're going to represent everyone with just one big sort of like this, right? So we have everyone here. Okay, so the overall weight of these people, right, everyone is going to have a specific weight that will be acting down, right? So their weight is going to be equal to mg. So their weight will be equal to their mass, which is the total mass, right, which is 78 times 25, because there are 25 of them, times 9.81. So this is basically the weight that is acting down. Then whenever we're on a slope, we can resolve it into two angles. We can resolve it in this direction, then we can resolve it in this specific direction. And I want you to know that when you're on a slope, the direction that will be along the slope will be mg, right, mg sine theta. Then the direction that will be here will just be mg cos theta, because if we're angle of 40 degrees here we're also going to have an angle of 40 degrees. Understand that whenever you have an inclined plane, the angle that will be moving along the plane will be mg sine theta, sort of the component along the plane. The component that will be inside the plane will be mg cos theta, because the angle of that plane will be the angle that will be coming from that line to that specific line. Okay, so it means that if we're going to have a force of mg cos sine theta, for the accelerator to move these people up, it's supposed to provide a force that is going to oppose mg sine theta. So the force that is supposed to be provided by the escalator should be equal to mg sine theta, not more, not less, because the speed is actually constant. So it means that for me to find my power, I know that my power is my work done divided by time, but work done is actually the force times the distance d divided by time. Hence the distance divided by time will actually be velocity. So power will be my force times my velocity. But in this case, I've said that my force is actually mg sine theta. This is the force exerted by the escalator times the velocity, which is v, which is actually 4.3. Okay, so if we have here, we have 78 times 25 times sine of 40 times 4.3. And then this is essentially just going to give me the answer, the power that I need. Which is about, I don't know, 52,873, stuff like that. So just going to be 53,000 or 53 kilowatts. The correct answer will be C. An elastic cord of unstretched length 16 centimeters and cross-sectional area 2.0 times 10 to the power of -6 is held horizontally by two smooth pins at a distance 8 centimeters apart. The cord obeys a law created by this guy Robert Hooke. Those physicists were really smart, right? So this guy created a law, Hooke's law, which says that the force is directly proportional to the extension, right? And then a load of mass 0.40 kgs is suspended on the cord. The angle between two sides is 60 degrees. What is the Young modulus of the cord? So you want to solve this problem. You're seeing it for the first time. How are you going to start? That's basically why we're here, right? So I hope you have tried it out. It's a very interesting question, and you know, it prompts you to think on your feet. So the Young modulus, let's start from principles. What do we know? Always break down physics questions from fundamentals, right? Start from the first principles. Young modulus is basically your stress divided by strain. This is where we start. What do you know, right? But what do I know? I know that my stress is basically my force over my area. So when a wire is being stressed, when it's under stress, right? It's not like humans when humans are stressed out, right? This is when a wire is stressed. It's because it has experienced a certain force over a certain area. And for it to be strained, for us to see that it was stressed, it's going to experience a strain with an extension per unit length. So it basically means my Young modulus will be my force over my area divided by my extension over my length. And then here I'll just have FL divided by AX. So in order for me to make this calculation, I need to ask myself, what is F? I need to ask myself, what is L? I need to ask myself, what is A? I need to ask myself, what is X? When all these answers are completed, or when all these requirements are met, I've found my answer. Let's first start from top to bottom. What is my F? I don't even know where to start, so I'm not gonna, figure out what the F is. What is my L? This is my length, my total length. Where is it? Here. My total length is 16 centimeters. So that's basically 0.16 meters, right? 16 centimeters. Okay. What is my area? My area, I've been given it here. Oh, they're so nice. 2.0 times 10 to the power of -6 meters squared. Okay. What is my extension? Again, I'm not given. So the trick part of this question is finding F and finding X. So that's what we're going to do here, right? We're going to first find F on this side, then we're going to find X on this side. And after I'm done with that, I just plug in my values, mathematical manipulation, and voila, I have my answer. Okay. For me to find X, I need to think, guys. Physics is about thinking. If I have 8 centimeters here, okay, when it's unstretched, it also means I have 8 centimeters on the top. So in total, I have 16 centimeters, which is what the question had told me. But look at this. I've put a mass here, and my wire has extended. It was supposed to be 16 centimeters, but look at this. There's 8 here, there's 8 here, and there's a whole length which is here, which hasn't been accounted for, right? And since I have 60 degrees here, and 8 and 8, it probably means that there's also going to be 60 degrees here, okay, and then there's also going to be 60 degrees here. So it's sort of an equilateral triangle that we have formed. Two similar sides, an angle of 60, that has to be an equilateral triangle, okay? So it means that we're going to have 8 centimeters that will be over here, right? So my extension will be my new length, okay, minus my old length. That's basically how I find my extension. My new length is I have 8 here, I have 8 here, and I have 8 here. So it's 8 plus 8 plus 8, 24. My old length is 8 plus 8, 16. The difference will be 8 centimeters. So it is extended by 8 centimeters. So my extension will be 8 centimeters, which is 0.08 meters. Cool. Then for me to find my force, this is basically my tension. You need to know, because we want to find the Young modulus of the core material. So the force that is in question is actually the tension that is in this material. So my tension would just be this specific tension. So this is where it was quite tricky. My tension would be this tension in the cord right here. How do I find it? Well, there are two methods. Well, there is one method. I think there's only one method, right? So well, there could be two. I mean, it depends with how physicists work it out. Okay, so the weight is acting down, right? Essentially, if you look at this question, the weight is acting down, which is a mass of 0.40. So the weight is going to be equal to 0.40 times 9.81. So this is the weight that is acting down. Then our tension, we can resolve our tension into two components, right? If we're to resolve our tension, right, our tension is like this. If we're to resolve our tension into two specific components, what is going to happen is that we're going to have 30 degrees on this side, okay, and then we're going to have 30 degrees on that other side. Then this is T. So if you're to form a little triangle, this is going to be the adjacent, this is the hypotenuse. So T will be equal to the hypotenuse, times cos 30, because if you want to find the adjacent, it's just your hypotenuse times cos of something, right? So this is going to be T cos 30 on this side, right? But also going to have T cos 30 on this other side. So both of them combined will give you 2T cos of 30. So we haven't done anything fancy, we've just resolved those two forces, they come together, 2T cos 30. Okay, but this thing is not moving down or doing anything, it's stationary. So it probably means that the resultant force is going to be 0. So for me to find my extension, I will just say that 2T cos of 30 should be equal to 0.40 times 9.81. Okay, so it means that my T will be equal to 0.40 times 9.81 divided by 2 times cos of 30. So if you do your computation, your tension would just be 2.2655 and so forth newtons. So it means that for me to find my Young modulus, we are now done. We have everything. I have F, which is 2.2655 newtons. I have F, 2.2655. I have L, 0.16. I have A, 2.0 times 10 to the power of negative 6. What is my X? 0.08. If I compute this, I'm going to get 2.3 times 10 to the power of 6 pascals. And the correct answer has to be C. So this was a pretty lengthy thing, but you just had to think. First, start from the first principles. What is the equation, and how can you be able to find everything that follows? Hope it makes sense. 19. A student is investigating, very curious student, lovely physicist, was investigating the mechanical properties of a metal. He applies different loads to a long thin wire up to its breaking point and measures the extension. He then plots a graph of stress against strain. The student repeats the experiment with a wire made from the same material, pays special emphasis to same, with twice the original length and half the diameter. Okay, so this is something that you just need to know, is that for the same material, your Young modulus is the same. It doesn't change. The Young modulus is the same for whatever material you have. As long as there is the same material, the Young modulus is going to be the same. And then I know that the Young modulus is basically from the previous question, guys. We talked about this. Stress over strain, right? That's so interesting, because we're just making relations. The previous question actually asked us something about the Young modulus, right? And then you know that the Young modulus is stress over strain. So it means that the gradient of this graph is basically the Young modulus, because it's the ratio of stress to strain. And I've said the Young modulus is the same for the same material. So if we're going to put a graph for another metal with the same material, it basically means the gradient should be the same because the Young modulus is the same. So the graph shouldn't change. It should be the exact same graph. Essentially, that is all you needed to do, right? Here we have 0, 20, 40. The x's have changed here, so that's wrong. Here also have 20 here. The x's have changed. Here we have 0, 4, 8, 12. But if you look at 10, here we have at 10 we have about 8. But then if you look at this graph, we have 0, 1, 2, 3, 4. At 10 we have about 2. So the only left answer will be B, right? Because at 10 we have 2. At 20 we have about 2 point something. Question 20. Which statement describes what is meant by plastic deformation of a material? Plastic deformation basically means that a material does not return to its original length when the extending force is removed. So if you remove the extending force, it will not return to its original length. That basically tells you that is experienced plastic deformation. So the correct answer will be B. Question 21. A stationary wave is moving along a rope, 2 points x and y. On a rope are a quarter of a wavelength apart from each other. Which statement is not possible for the 2 points x and y at any instant? So we have 2 points x and y, okay, like so. Then we have our little wave that is on this line like this, our stationary wave, okay. And then we have 2 points which are a quarter of a wavelength apart. So x will be here, this is half, so y should be here. They're a quarter of a wavelength apart. Which statement is not, pay particular key attention, is not possible? So it can't happen. They're both stationary. This is impossible. They can never be both stationary. This doesn't make sense, guys, because look at this. How is it possible that x and y can both be stationary? They are both moving in opposite directions. If y is moving up, x will be doing the opposite. If y is doing this, x will be doing that. So there's no point at any point that they are both going to be stationary. So A is wrong, or A is not possible. In this case, A will be our correct answer. If you look at B, they are displaced in opposite directions from their equilibrium position. It's possible. X and y are a quarter of a wavelength apart. So it means that x can be here, or maybe y can be here. They're still a quarter of a wavelength apart, right? But they're sort of displaced in a different orientation. If you look at something like that, right, you can basically see that they're displaced in opposite directions, right? And then you can, because one is up here and then the other one is up here, moving in opposite directions, you can tell that maybe this one will be moving up, or maybe this one will be moving down, or this one will be moving down, this one will be moving up. It's possible for them to be in opposite directions. It's also possible for them to have the same displacements from their equilibrium, because it's also possible for this displacement x to be equal to this other displacement x for that other particle. So again, it's nothing fancy. It's also possible for all those three scenarios to be correct. Move on to question 22. Two progressive waves are meeting as a specific point P. The variation with time t of the displacement of each wave is shown in this graph. What is the phase difference between the two waves at a point? So phase difference is actually calculated using a very special equation. So phase difference phi will be equal to 360 degrees. Sometimes a textbook might say 2 pi, right? Times the time over the period. So this is the time, or it can also be calculated by saying, right, 360 degrees or 2 pi times x divided by the extension. So the wavelength divided by the wavelength, right? So what you're doing is this is the time difference, or this is the actual distance difference between points that are in phase. Points that are in phase. What does this mean? It means that they have the same displacement. The same displacement at the same time. Get that, guys? If things have the same displacement at the same time, they're in phase. So if you find the distance or the time between them, you divide it by the period of that wave, or the period of those waves. You multiply by 360. You then find the phase difference. How out of phase are two waves out of each other? How different? How much is one wave lagging behind another? But this t is only between particles that are close to each other. If you have two waves, this t is between particles that are close to each other. So if you're here, Let's first start with the easy one. Since it's a time, we first have to find the period. Time taken for one complete wave cycle is going to be up and down like this. So our period is going to be 0.8 seconds. We're now over there. Okay, so it means that we're just going to have 360, right? If you're using this equation, you're just going to have 360 times your period, which is 0.8. Now we want to find the time difference between points that are going to be in phase. So if you look at this, we have this specific point. We can just find any point we want. If I have this specific point, the next point that is experiencing that same displacement at the same time on the next wave will be this point. If we do that again, if we go up, this point and then this point. If we go down, this point and then that point that will follow. Those are what I'll call consecutive points that are in phase. So if you find the time difference, you have 0.6, you have 0.3, the difference will just be 0.3. You punch this on your calculator, you're going to get 135 degrees. So it means that the phase difference will just be the 135 degrees. What you're doing is you're finding that one wave is lagging behind one another, or they're out of phase by 135 degrees. Question 23. We're given a microphone that is connected to a cathode ray oscilloscope that is then placed in front of a loudspeaker, and then the trace is seen. Three things: microphone, cathode ray oscilloscope, and the loudspeaker. The time-based setting is 0.5 milliseconds, then the Y plate sensitivity is 0.2. We just want to find the frequency, and we want to find the amplitude of this trace. So the amplitude is pretty easy for us to calculate, because the amplitude is essentially here, right? You go to the middle point like so, okay, and then when you go to the middle point, you just calculate the how many boxes have you gone up, because it's the maximum displacement, right? So your amplitude is basically just your maximum displacement. So by finding it, you just have to count from the equilibrium position here. Your maximum displacement is here. So when we're here, we have 1, 2, 3. We have 3 squares that we have traveled. So it means that in this case, our amplitude will just be 3 centimeters. But you have seen here that 0.2 on the y-axis, the y plate, 0.2 millivolts symbolizes 1 centimeter. So if you have 3 centimeters, our amplitude will just be 3 times 0.2, which is just 0.6 millivolts. So it's either this answer or that answer. And then if you look at our period, because we know that our frequency is the number of complete wave cycles per unit time, so we know that our frequency is just 1 over our period t. So our period is the time taken for one complete wave cycle. So if we take this point as a reference, we just want to find a point that can give me specific centimeters. Then I go up, I go down, I go up. This is one complete wave cycle, because after this I'm going up and I'm going down. I'm repeating that same motion. So that's a complete wave cycle. So it means that if I start at this point, I have 1 here, I have 2, I have 3, I have 4, I have 5, I have 6. So I basically have 6 centimeters. Okay, but I know that 0.5 milliseconds is for 1 centimeter. So it means that my period will just be 1 over 6 times 0.5. But in milliseconds, milli means times 10 to the power of -3. So it means that if you punch this on your calculator, your frequency is going to be 330 meters per second. Hertz. 330 hertz. The correct answer is going to be A. Very important. Just find how many centimeters make up a period, find the time, and then you can be able to find the frequency. Question 24. The diagram shows an experiment to produce a stationary wave in an air column. We're given a tuning fork that is placed above the column, vibrates, and produces a sound wave. The length of the air can be varied by altering the volume of the water in the cube. The tube is then filled and allowed water to run it. The first 2 stationary waves occur when the lengths are 0.14 and 0.42. What is the wavelength of the sound wave? Okay, the first stationary wave. A stationary wave consists of 2 things: an antinode and a node. So the first stationary wave, whenever you're drawing it, is going to start at the mouth, because since it's open, we're going to have an antinode, maximum displacement. It's going to go up like so, and then up like so. So this is the first wave that we're going to experience, right? Then if you take it, we're going to place it here. The second wavelength, or the second stationary wave that we're going to form, it's basically just going to have an extra node. So we keep on adding a node every single time that we form a new stationary wave. So if we're going to do this, it's going to be like this. We only had one node in this instance, so we're going to add another one like so. Right, so we're going to add another node, and in the process we've just created an antinode, right? So we're just going to have something like so. Okay, like so. So if you take this, then you compare these two side by side, what is only different is this part. Okay, this is the part that is only different. And if you look at the lengths, this whole length is actually 0.14. Then this whole length is actually 0.42. Right, so that's the differences in the length. The other one is 0.14, the other one is 0.42. So it means that from this node to that node is just going to be 0.42 minus 0.14, which is just essentially 0.28 meters. But we know that if you have a wave like this from a node to another node, that is going to be one wavelength lambda. So if you have a node to a node, it's going to be half lambda. So half lambda is just going to be equal to 0.28. So lambda is going to be equal to 0.28 by 2. So you're going to get 0.56 meters. The correct answer would be D. 25. A stationary person measures the speed and wavelength of sound from a horn of a stationary vehicle. We have a vehicle and the driver is busy sounding the horn. The person repeats the measurements when the vehicle is approaching, right, but at a constant speed, which will describe the measured wavelength and the measured speed of the sound wave from the moving vehicle when compared with the sound wave of the stationary vehicle. Very important. So, does the speed of sound change if a stationary vehicle moves? That doesn't make sense. Sound is constant. The speed of sound is always going to be the same. Right? That's one thing we can always count on. You're not going to wake up tomorrow and sound is like 500 meters per second, right? That will never happen. So the speed of sound is always going to be the same. But what's going to change is the wavelength of that sound when it's approaching. So whenever it's approaching, the waves get swashed together, right? As it's approaching, the waves get swashed together. Hence, the wavelength actually becomes shorter, right? As it becomes shorter, since we know that V is equals to F lambda, since V is constant, if the wavelength becomes shorter, it means that the frequency will actually increase. And that explains why you're moving towards an object, the frequency actually increases because the waves are getting more compressed. Hence, the number of wave cycles that you're performing will now be greater. So the frequency will actually be greater. Okay. Question 26. If you look on the graph, I'm showing you, if you look on the screen, I'm showing you all the different, ranges that you'll be asked in examination. This is from an official Cambridge textbook that you are assessed on, right? So, as you can see, gamma rays fit between 10 to the power of negative 14, sure. X-rays, sure. Infrared, yes. Microwave, 10 to the power of negative 2, that's correct. Radio wave, that's correct. So the correct answer will be A. Move on to question number 27. We're given two progressive waves that meet at a point. So we have one wave, like so, another wave, like so. Then they meet. Hello. They greet each other. I don't know what waves do when they meet, right? But they're sort of meeting at a point. And then we want to find out if superposition is going to occur. So basically, superposition, as it's described, is basically the algebraic sum, right? The algebraic sum of the individual displacements, right? Of the individual displacements of a wave. So it's the individual displacement. So we're adding them up. So we want to find out which one of these conditions must be met for us to be able to make waves meet. Okay. For A, the waves must be coherent. Coherent means that they have a constant phase difference. Okay. This is more of a condition actually for interference than it is a condition for superposition. So since this is a condition for interference, it means that A is going to be wrong, because superposition is not interference. We need waves to have a constant phase difference, sure, but we don't really need that to just have an algebraic sum. With superposition, we're just adding waves. Even if they have dysregular, one is like it goes up slowly, like it's irregular, right? It's like, like this, right? We can still add them and get an algebraic sum. So we don't necessarily need waves to be coherent. B, waves must be of the same type. This is a must, right? That's why it is so correct. Why? If you have a transverse wave and a longitudinal wave, there is no way on Earth, there is no way that those two waves are going to add up and actually give you something, because they move in different direction. Longitudinal is parallel, transverse is perpendicular. So there's no way that they're ever going to meet, right, and actually give you something that makes sense. For C, the waves must be traveling in opposite directions. Sure, but it depends. If they have different speeds, even in the same direction, they probably meet, right, if one is faster than the other. So C is out. The waves must meet in phase. Again, this is more for stationary waves than it is for superposition, and this is also, again, in phase, is also more for interference than it is for anything else. Question 28. So the correct answer is B. A hill separates a TV transmitter from a house. The transmitter cannot be seen. However, television is good TV reception. Which wave effect could the television signal reach the house? So we just want waves that are producing here, so that they can able to diffract across the mountain and reach this range which they went normally at. So when they reach this region, it probably means that what have the waves done? They have diffracted. So the effect is going to be diffraction. Very important for you to be thinking of that. Question 29. Particular scenario, we're trying to demonstrate two source interference using current light of a single wavelength. An interference pattern is displayed. An interference pattern is observed 3 meters away. So the central fringe is at Q, the second bright fringe is at P. What is the distance between Q and P? Right, so what do we know? Let's always start with what you know. Lambda is equal to AX divided by D, right? And we know that whenever we're making these calculations, our D is coming from the central fringe, from one fringe to another fringe, and that's, our X. And we know that our X is coming from one fringe, which is bright, to another fringe, which is bright. If it's dark, it's from one dark fringe to another dark fringe, but they have to be consecutive. Then our D is this specific distance. Our A is basically this distance between the two slits. Then our lambda is our, essentially just our wavelength, right? So if you want to find the X, which is just between Q and this midpoint, let's just say M, right, that will be X. Then if you want to go from M to P, that would be another X. So it means that from Q to P, that is basically 2X. Okay, so we just want to find X first. So you know that X will be equal to D lambda divided by A. Our D is 3 times our lambda, which is from the question, we don't know, so we're just leaving it as it is. And then our A, which is our separation, which is 1 times 10 to the power of negative 3. Then this is our X. If we divide this, this is basically 3000 lambda. So it means that 2X would just be 2 times 3000 lambda, and that's going to be 6000 lambda, which is 6 times 10 to the power of 3 lambda. So the correct answer will be A. Question 30. Light waves of wavelength lambda, we're given wavelength, is incident normally on a diffraction grating. Whenever you see the word grating, this is my law. I drop everything, I drop my pen down, and I write d sine theta is equal to n lambda. Whenever I see a diffraction grating, somehow I have to use this equation. I always know it, right? The angle between the second order, pay attention to the word second order, and the normal to the grating is theta. The variation with sine of theta is shown on the graph. How many lines per millimeter are on the diffraction grating? Okay, so using this equation, d basically refers to the how big one line is on this diffraction grating. A diffraction grating basically consists of multiple lines, so d is just how small is one line. But if you look at this is a graph of lambda. Again, it's sine theta. So it means that lambda will be equal to d over n times sine theta. So essentially, this tells me that d over n is just my gradient, right? My gradient of this specific graph. So in order for me to find my gradient, this is the ratio, the change. In order for me to find my gradient, this is just, a specific ratio that I'm just going to find. So my gradient will be equal to my change in y, right? My change in y, which is 250 times 10 to the power of negative 9 divided by my sine theta, which is 0.2. So if I divide this is just going to give me 1.25 times 10 to the power of negative 6. Okay, times 10 to the power of negative 6. So it means that d over n will be equal to this. So my d will be equal to 2 times 1.25 times 10 to the power of negative 6. And then this would be 2.5 times 10 to the power of negative 6 meters. So one line has a thickness of 2.5 times 10 to the power of negative 6. So if one line has this, what about in 1 millimeter? In 1 millimeter, how many lines do we have? So it's just a matter of division. 1 times 10 to the power of negative 3 divided by 2.5 times 10 to the power of negative 6. This is just going to give you 400. So it means that in 1 millimeter, you're going to have 400 lines that are going to fit. So the correct answer would be A. 31, that this is electric fields, we don't do it. 32, electric fields, we also don't do it. 32, the number density. Again, this is one of those scenarios, guys. Whenever I see a word, I drop my things down. Whenever I see the word number density, I know this is going to come up. I is equals to AN VQ. Some textbook will say E. Same thing, elementary charge, right? Where in this specific scenario, I is your current. Okay, and then A is your area. Any area? No. Your cross-sectional area. Then N is your number density. And then Q is your elementary charge. And then V is what we call the drift velocity. Electrons are so cool. They drift. They don't just move, they drift, right? So the average drift speed or velocity will be represented by V, right? Okay, so we want to find the average drift speed of the free electrons in the wire when the current is 0.57. So we just want to find V. So V will be equal to I divided by A times N times Q. Okay, so your V will be equal to your I, which is 0.57, your area, which is pi d squared over 4. Why? Because area is pi r squared, but your diameter is equals to 2 times your radius, so r is equals to d over 2. So pi d over 2, which is d squared over 4, because 2 squared. So here we have pi your d, which is 0.42 times 10 to the power of negative 3. All of that are squared divided by 4 times n, which is 8.0 times 10 to the power of 28. Elementary charge 1.6 times 10 to the power of negative 19. Then that's going to give me a value of V, which is just essentially going to be 3.2 approx times 10 to the power of negative 4. The correct answer is going to be D. 34. We have gone to the kitchen, and we're in a kitchen and we're given an electric kettle, right? That is rated 2000 watts. And this describes the power that is supplied to the heating coil. So there's a coil that will be inside that kettle. And then we're told that that coil has a resistance of 5 kilo ohms. What is the current in the coil? Okay, what do we know? I know that power is work done per unit time. That is what I know, right? So we want to derive anything. But I know that potential difference is basically the work done per unit charge. So the work done will be equal to VQ. So power will be equal to VQ divided by T. But I know that I is equals to QT, right? Because Q is equal to IT. So I will be equal to Q over T. So P will be equal to VI, right? So power will be equal to your everyday voltage times your current. Okay, and that's a very, very important deduction that's going to help us whenever we are making calculations. So we now know that P is equal to VI. But I know that V is equal to IR. So it means that if I do my substitutions, P will be equal to I squared R. So if I want to find I, given resistance, it will just be P divided by R, the square root of that. So it's the square root of, what is my P? 2000. What is my R? 5000. What current do I get? 0.63 amps. As simple as that. The correct answer will be B. 35. A conductor. Conductor, something that just allows current to flow through at ease. Consists of 3 wires that is connected in series one after the other. Like, a normal series that you watch consisting of episodes, episode 1, episode 2, episode 3, right? The wires are all made of the same metal, but have different cross-sectional areas. There is a current I in the conductor. Point Y on the conductor is at 0 potential, which graph best shows the variation of potential V with a distance along the conductor. Okay, so what do we know? I know that resistance is equal to rho L divided by A, resistivity times length over area. And why am I trying to use this is because I've been told that they have different cross-sectional areas. So I've just been perusing across the different formulas that I know, and this one is the one that came to mind. Because I know that the length of these guys is constant. The length of these guys is not changing. And the resistivity doesn't change because it's the same material. So that means I can have a relationship that R will be inversely proportional to the area. Okay? If I look at the first scenario, I have a bigger cross-sectional area. From this relationship, I should have a small r, right? And then here, I should have a big R. Then here, since a very small area, I should have the biggest R, right? And if you know anything about resistance, is that the voltage essentially, or the PD, is distributed, right? Is distributed based on resistance, right? The bigger the resistance you have, the bigger the voltage you get. The bigger the resistance you have, the bigger the voltage you get. The smaller the resistance you have, the smaller the voltage you get, right? So it means that for the first part, the potential drop that we're going to experience has to be small. Why? Because it has a small resistance, and at the end our drop has to be big. Why? Because it has a bigger resistance. Okay, so if you start with A, and I want you to testify for yourself, right? If you go from this point to this point, right, like so, this is a specific drop that I have, right? And then if I were to go from this point to this other point, right? So let's just first compare from this point to this other point. This is again another drop that I have. Okay, if I go to B, if I'm to go from this point to that other point, that is again another drop, that I'm going to experience. So from this point to this point, this is a drop that I'm going to experience, like so. And then this is also another drop that I'm going to experience, right? From this point to this point. Like so. From this point to this point, right? And then for C and D, there is literally no drop that is actually occurring at all, right? For C and D, yeah, there's no drop. So they're probably wrong because potential has to be dropped, right? Okay, if we start with A, we say that there should be a small drop for the first one, a slightly bigger drop, and then the biggest drop, right? If you look at here, here we have a small drop. That makes sense, right? A small drop in potential difference. And here we have a slightly bigger drop. And then here we have the biggest drop. Okay, the same here. We have a very big drop, a slightly smaller drop, the smallest drop. Okay, and then what I meant to say is that whenever we have a small resistance, we're going to have a small drop, The biggest resistance, the biggest drop. So correct answer obviously has to be A, because B is the exact opposite. They can give you a similar question in your paper, just with flipped scenarios. You should just be able to apply this stuff. 36. A cell consists of electromotive force E and internal resistance 0.50. The maximum power that can be supplied to the resistor without it overheating is 0.50. What is the maximum value of E? So E is the EMF, and E is distributed accordingly. So it means that you get some V, you get some V. So both of these guys get a V, and they get a share of E. So what I know is that my E will be equal to the current that passes through, because potential difference is current times resistance. So it's the current that passes through the internal resistance times the small letter resistance plus the current that passes through the big resistor times the big resistance. So my E will just be equal to I R plus R. So it means that my E max will just be equal to my maximum current, right? My R is 4.7, my that one is 0.5. So my E max will be equal to my I max times 4.7 plus 0.5, which is just 5.2, right? And I want to find I max. So I know that when things are in series, the current is the same. Okay, so it means that if I'm going to use this information that I'm given the maximum power, which is 0.50, then I'm given this resistance, I can basically find the current that will be flowing. Okay, and how do I do that? Well, I know this is a fact. I know that, but I know that I max, right, from power is equal to I squared times R. Therefore, I max will be equal to the square root of the maximum power divided by the resistance. Okay, so it's the square root of the maximum power, which is 0.50, the resistance that I have, which is the resistor from this question, the resistor, which is 4.7. So it means that my I max from this question is going to be about 0.32616 and stuff like that, right? So if we go back to my question, it would mean that my E max would just be equal to 0.32616 and stuff like that times 5.2. And this is going to give me 1.69, something like that, which is just 1.70 volts. So the correct answer will be C. So I just started by the fact that E is distributed, then I can find I, because I max times R plus R, and I max I can find it by using the information that I had been given. Okay, so that's physics. Use the information that you're given to find the information that you need. 37, we have Kirchhoff, very famous scientist and physicist, who came up with two laws that explain the movement of electricity. Essentially, you have Kirchhoff's first law and Kirchhoff's second law that are linked to the conservation of physical quantities. So Kirchhoff's first law talks of the conservation of charge. Second law talks of the conservation of energy. The correct answer would be A. 38. In the circuit X is a variable resistor, so that's a variable resistor. So you can sort of change its resistance from 5 to 500. The electromotive force EMF of the battery is 12, and it has negligible internal resistance. What is the maximum range of values of the potential difference across the output, right? So we're given a variable resistor, and we can change its resistance from 5 to 500, right? What you need to know, this is a must, something that you must know and appreciate, is that PD is shared on the basis, right, on the basis of resistance. The bigger the resistance you have, the bigger the potential difference that you have, right? So if you're big, you're gonna get more, essentially, right? More potential drop is gonna be dropped when I'm moving across you. So we can use what you call the potential divider formula for us to find how much potential is going to go into one thing. So the potential divider is just saying what is your resistance divided by the total resistance times the whatever we have that will determine your share, right? For example, if you have 3 people and you want to find out how much one person gets, you're just saying 1 person divided by 3 times the thing that you want to share. Let's say you have a cake that you want to share, right? So it's one person. You have 3 cakes that you want to share, right? And you have 3 people. So it's going to be 1 person divided by 3 times 3 cakes. Then you're going to get 1 cake per person. So in the similar sense, if you want to find out how much potential one resistor gets, in this case, we're going to vary it from 5 to 500 so that we can get an output here. We're just going to start with 5. So it means if we have 5 divided by 5, and we're sharing it with that 40, which is over here. So it's 5 plus 40 times, what are we sharing? We're sharing 12. That means the 5 will get 1.3 volts. Then when we have 500, with just 500 plus 40 times 12, 500 is going to be stingy, and it's going to get 11.1 volts. So it means that the range, right, the range of what I get will be just from 11.1 to 1.3 volts. So the correct answer has to be A. Question 39. An unstable nucleus goes through successive decays. One decay after another, it doesn't stop until it becomes a final stable nucleus. It's peaceful, living a peaceful life. So the initial nucleus and the final nucleus are very important things. They are isotopes of each other. What is an isotope, you might ask? Well, isotopes are elements. We're doing some chemistry now, or some physics. I mean, elements with the same proton number, but a different neutron number. But different neutron number. So we're going to start off with an element, right? Let's say X with 20 and 10, nuclear number of 20, proton number of 10. And if it undergoes alpha decay, it's going to form a daughter. Okay, it's going to form a daughter that has 16, and then here it's going to have 8, Y plus 4, 2, and then an alpha. Okay, and then it's going to undergo beta minus decay so that we reach an isotope that is the same proton number. So we're going to have 16, 9, Z plus 0, negative 1, and beta negative. Okay, then this beta negative is going to undergo another beta negative. We have 16, we have 10, we have, I don't know, I'm out of letters here. I don't know, M plus 0, negative 1, and beta negative. So how many have you lost? Let's count together. 1 of beta particle, 2 beta particle, 3 beta 2 beta particles and 1 alpha particle, right? So we have 2 beta negative particle and 1 alpha particle. The correct answer would be B. Number 40, a hadron. What is a hadron? A particle that experiences a strong nuclear force. It is found in a nucleus. This can be a lot of things. It can be a neutron. It can be a proton. A hadron is just a lot of stuff, right? Is a charge of negative E and is composed of 3 quarks, 1, 2, 3. What could be the quark combination of a specific hadron? Okay. One of the things that I know is that for a specific hadron that you might be given in a specific question that you'll be trying to solve, you just have to make a combination of all these quarks, and when you make that combination, you can therefore be able to sort of make a prediction. Okay, sort of something like that, right? So one of the things that I know is that I've about 3 generations with different levels of quarks. I have an up quark, then I have a down quark. We go up, we go down. I have a top quark. You're at the top, you're gonna be at the bottom quark. I have a strange quark, very strange. Then I have a charming quark, a charm quark. Right, so these are the different quarks that we have, and they also have different charges, different elementary charges. An up quark is up, so it's going to be positive, it's up there, right, with positive 2 over 3 E. A top quark, again, is also up there with positive 2 over 3 E, it's at the top. A down quark, negative 1 over 3 E. Bottom quark at the bottom, negative 1 over 3 E. But I always faced the challenge when I was doing physics between discerning strange and charm. Which one gets positive 2 over 3, which one gets negative 2 over 3. Then I figured a trick. Strange has an N, right? Strange has an N. It's strange that there's an N in strange, right?
Okay, so strange has that n which stands for negative. That's why they put it there, so that it helps you in memorizing the stuff, right? So strange is an n that stands for negative, so it's going to be negative, and you always know that if it's a negative, it's accompanied by a smaller number, negative 1 over 3e. Charm quark is going to be therefore positive 2 over 3e. So it means that for here I have three stranges, which is negative 1 over 3 minus 1 over 3 minus 1 over 3. That's going to be negative e. So the correct answer has to be A. And this marks the end of my video. I really hope that it was helpful. If there's anything that was challenging or any specific area that you need assistance on, please do put in the comment section below and I'll be happy to address it. Thank you guys for watching and making it towards this very end. I hope that you'll be able to succeed in all your endeavors. Thank you again for watching, and I'll see you in the next one.